Can anyone hear what I'm saying? Testing. One. Green dot. Looks like it sounds on. Any testing for the online community? 1, 2, 3.
Can you hear us over Zoom? Testing. What are they saying? Still? They can hear us.
They can hear both of us
this
now.
mic?
Can you hear Adam speaking? Yes or no? I've got a lovely bunch of coconuts.
Yes.
CityDB. What's the YouTube link doing now? Just out of curiosity. Oh, what it's getting recorded to? Okay. Oh, no, that's fine. Okay. Great. Can I ask a question first? Do I get any introduction from Michael or you guys beforehand? Sorry, just in terms of like how much do I actually say on this slide? Because normally it's a, hey, I'm Adam, let's go. Great, cool. Sounds good. All right. Well, thank you all for being here today and for your time this afternoon, listening to my dress rehearsal for this talk. I'm Adam Hoffman. I'm a staff scientist here at Slack, and we're going to be talking about catalytic characterization using X-rays. But to get started, depending upon what Michael covers here, my life is summarized by Interstate 80. So I was originally born and raised in born and raised in Lebanon, New Jersey, growing up on a small farm. I did my bachelor's and my master's in chemical engineering at Villanova University, where I took a strong interest in understanding how to transfer alternative waste streams into alternative fuels, looking at biodiesel production and then essentially methane generation from that. I was encouraged by my professors at that point. If I really wanted to understand catalysis science, I should seek out a man named Bruce Gates, which I skipped the rest of the country and moved to California, where I got my PhD in chemical engineering at UC Davis. This was atomistic understandings of catalysts, which we'll talk more about today, and my first experience with national labs and synchrotron science, the other part of today. Post-PhD, I moved here to Slack, where I got my postdoc, and have slowly been working my way up to the staff scientist position at SSRL. To get started, I would like to thank all of my collaborators, faculty, staff, and students here, and I want to pose the question of what do they all have in common? They are all interested in catalysis science. This is because catalysts make the world go round. Roughly 90% of the items you interact with in a day either use a catalyst or had a catalyst used in their synthesis. This spans everywhere from fuel for your car, textiles for clothing, pharmaceuticals for drugs, all the way to agriculture. It's roughly a 35% global domestic product funding stream. And to give you a scale of how much catalysis can, or catalysts and catalysis can impact us as a society, I present to you a graph with the blue curve representing the world population. You see that there's a sudden change in the rate of population growth somewhere around 1950, and an orange curve on there that corresponds to the amount of ammonia that the globe produces. Ammonia is the first reaction step created by the Haber-Bosch process, a catalytic reaction. Going back one, sorry. Haber-Bosch process that is a catalytic reaction, and what is the building step for fertilizer. Okay, and so we can see that our ability to produce ammonia is what is actually supporting our current population. And the bigger, surprising number with this is that the amount of energy we need to drive this reaction forward is approximately 2% of the world's energy production per year. It's massive. And so when you start thinking about maybe a product you don't see, there are challenges associated with it, and there are opportunities for us as a community in catalysis science to better optimize systems. So for the DOE and to the community at large, there are three major challenges for us. It's our dependence on fossil fuels. Can we use catalysis to change this? Can we use catalysis to drive different energy sectors? And because catalysts are made up of multiple elements on the periodic table, most of them being in low abundance, meaning we either have to do a lot of mining or we don't have a large amount of them to use, period. How do we use them in a more efficient manner? And so to tackle these, we have to understand at an atomistic level how we understand how the catalyst behaves so that we can optimize for the next generation of materials. So I've used a few terms that you guys probably aren't aware of. So we're going to talk about catalysis and catalyst first. Catalysis is the act of accelerating a chemical reaction. In high school chemistry, you might have seen something like A plus B goes to C plus D. I have X plus Y, my reactants, go to Z, my product. Under the arrow, when you get further along in school, you might see that you have conditions at which this occurs or what catalyst is used for it. You then see that this is associated with an energy diagram where you have reactants on one side, products on the other, and you have a line that represents an energy input, a barrier you have to overcome to drive the reaction forward. The black curve represents this barrier if you don't have a catalyst. The red curve represents it when you have a catalyst. We see that there's a difference in the maximum intensity. This is energy savings, and it has a few key points that are important to us. One, a reaction that might not be possible suddenly is. We can save energy, so we can operate at lower temperatures or put less input in, or if reactants X and Y can make multiple products, the catalyst allows us to maybe shift the way the reaction behaves so we get a target product instead. In cartoon form, you can think of this as Wile E. Coyote climbing the slow mountain or the steep mountain. It takes a lot of energy and effort to do this. Or with the catalyst, you're the zippy roadrunner going straight through the tunnel. Cartoon aside, let's go back to ammonia and talk about the Haber-Bosch process and put a number on it to give you a sense of scale here. Ammonia synthesis is just reacting nitrogen gas plus hydrogen gas to get ammonia. You have to do this at temperature, and the catalytic process these days uses an iron catalyst. If we remove the iron catalyst, we have to heat this thing up to 6,000 Celsius, the surface temperature of the sun, to drive this reaction forward. As soon as we put the iron catalyst in the presence of these gases, we only have to heat up to a modest 500 degrees Celsius, the temperature of your campfire. So we went from something that is unobtainable on Earth to something that is 2% of our energy production to generate a product. Catalysts come in all different forms, and the one I mostly work with is a supported metal catalyst. The example closest to you in most of your life is your catalytic converter in your car. It's this ceramic cylinder that looks like a bunch of packed straws. So if we take this catalytic converter out, we see that hydrocarbon, carbon monoxide, and NOx flow in. Something happens catalytically with this, and we get more benign, environmentally friendly products out. If we zoom in, we see these tiny straws allow the gas to flow through it, and if we zoom further in, we get this balls represent atoms, cartoon picture of what the surface looks like, where you have a metal or metals responsible for doing the catalytic reaction as the gas molecule flows over it, supported on a material called a support, which allows us to keep these metal sites away from one another. It's a way to optimize how we utilize metal. Scale-wise, to give you a sense of what we're looking at, your car is up until the millimeter scale, will go both about 5 meters long, and we start moving down to about 6 inches to a foot, depending upon brand of converter. The pore is about a millimeter, a 16th of an inch. That little metal blob, about 2 nanometers in size, about 100 million times difference in scale, is responsible for how your car makes emission control. And so to understand catalytic materials, we have to understand at the atomistic level how to control them and how to understand how they behave. But the challenge is metal-on support is an oversimplification. If I look at now thinking about how do I use carbon dioxide for the system, carbon dioxide is a potential fuel source. I can react it with hydrogen. I'm giving the case here. My catalyst is rhodium on titania, the demarcation under the arrow. If the rhodium is atomically dispersed, that means my little red rhodium circle here is one rhodium atom. If I flow my reactants over it, I make carbon monoxide as my major carbon product. If my rhodium atoms start sticking together on the surface, forming a little cluster or a nanoparticle, the chemistry completely changes. I now make methane. And so if I'm targeting one of these two, I want to understand how do I maintain or how do I track that structure? And so we know, first pass, structure greatly influences performance. If you go back to your school days, you might have been told that a catalyst is perfect. It does the same reaction over and over and over and over again. It's not quite true. They're really dynamic. And by dynamic, I mean with time, on my axis here, the amount of material I can make can decrease. So it deactivates. I make less product. The other option is, in my rhodium case on the previous slide, if I change my structure, maybe instead of CO, the orange curve decreasing, I make methane, the purple curve increasing. And these timescales, so we can make a different product. And the timescales here are varied. This could be occurring over seconds, or this could be occurring over years, depending upon the reaction. And so if we know that performance changes with time, we'd also like to show that structure changes with time so we can understand the two's relationship. And so we ask, how do we do this? Cool. And so I want to know how, as a researcher, how do I obtain this? And so the first thing is catalytic performance. This is the at-home experiment. At home to me is the right image, a little lab scale reactor where I have a tube filled with catalyst material, and I flow gases over the top and products come out the bottom and I quantify it. I learn things about how fast a reaction occurs, how temperature changes things, how pressure changes things. Industry, ExxonMobil, has a 10-story version of this, but instead of trying to understand the fundamentals, they use this to understand and make product. But they're black boxes. Reactants go in, products come out, and over time that changes, and so we can't see it. And so if we want to see it, we take a trip to the synchrotron. And so we'll cover more about a synchrotron moving forward, but to start us off, a synchrotron, they're almost always round or somewhat circular in shape, and they're high-powered electron storage rings. And what this enables us to do is generate X-ray radiation from the physics of moving an electron through a magnetic field. And then you'll see that there's a couple tangent lines off of my schematic here. We take those X-rays and we port them into these beam lines. And they have mirrors and optics that allow us to manipulate the direction of the X-rays. And at the very end, there's a little experimental station where we can perform a measurement on it. And it's a trip. So I talked about the playground. In grad school, I would go to the synchrotron 3 times a year, and it was the greatest experience of my time because I got to play with something I couldn't do it. And I compare it to a playground because you have to travel. There's very few people who work at them, but the community they support is global. You have to pick what ride you're going to go on. You have to pick your beamline, and you have to play the question of, am I tall enough to ride it? Or does this beamline make sense for the science I want to do? As soon as you're there, it's 24/7 nonstop experiments. You try to make the most of it. At the end of your time, you return. It could be with memories from playground. It could be with data from the synchrotron. And the biggest one for me was as soon as you got back to the home lab, you're talking about when are you going to come back to do the next experiment. So much fun. And so my playground is SSRL, the Stanford Synchrotron Radiation Light Source. We're a mid-sized synchrotron in the world of synchrotrons. We support 24 beamlines. So we have 24 of these little tangent lines coming out, and we have about 1,600 visiting researchers a year. They come for 3 or 4 days, make their measurements, and head home. It does a myriad of techniques, but there are three that really stick out for me in catalyst characterization. There's imaging. I can take a picture of my catalyst and see at the nanoscale what's happening. There's scattering, which we're going to start using C because it's less of a true picture and more of data. I can look at the crystalline structure. Or the one we'll focus on today is X-ray absorption spectroscopy, where I can actually see the electronic and atomistic structure of my material. And so what this means is if I think about electronic structure, you ask about where are the electrons. On the left here, the first pass we normally use is something for checking for oxidation state. For me, oxidation state is understanding of the metal of interest, how many electrons are kind of taken away from it. The common example when we think about oxidation state in the real world is rust. You have a nice copper metal clad roof. You go to Europe and you see that they're all green. With time, the metallic copper has oxidized into copper oxide. If you get into understanding how electrons arrange themselves around molecules, we can start thinking about symmetry. So if the purple atom is my atom of interest, I can look at the electronic structure and tell, are there 6 atoms arranged in kind of this pyramid structure? Or are there 4 atoms arranged in this caltrop D4 structure, depending upon the fandoms you're in? When I think about the atomistic structure, this is where are the atoms? This is, in my example of the rhodium and the isolated rhodium and the rhodium cluster, I can identify that the isolated rhodium I cannot detect, or I cannot model, or I cannot see another rhodium within a bonding distance. I might be able to see that it's interacting with the support. It's a connection that exists. Whereas on the rhodium nanoparticle, what I'm looking for to show there is that I actually see rhodium-rhodium interaction. I'm calling them interaction. They're bonds, but there are also other effects that help tell me how many of them are around there, and I can gain some insight as to how big of that particle there is based upon the number I determine of neighbors. What this actually looks like is a measurement. This is beamline 9.3 at SSRL. You see a bunch of cables and tubing, but what we're going to point out is the long tube moving from right to left points to a central area where you see a bunch of detectors all oriented at it, and that is where we mount our sample. During the measurement, I'm going to collect this bunch of squiggles, and this is me seeing my catalyst. It's described as having a pre-edge, this region from 7 to 7100, an edge step, this large seeming jump discontinuity, and then there are 2 regions of the wiggles that are of interest, the Zanes, X-ray absorption near edge structure, and the XAVs, extended X-ray absorption fine structure. Zanes represents my electronic interactions, the XAVs represents my atomistic. Going back and forth, I'd be remiss not to explain actually how the physics of this works, because it is quite fun. But the scale I've shown here is specifically for iron's 1s electron. What I do with the synchrotron is I know what element I'm interested in, and I can tune my X-ray energy to find an energy that matches with an electron inside my element. And so in my depiction on the left here, my HV, my light comes in. When it matches the frequency of this or matches the energy needed to excite the electron is excited out of the atom and into the continuum. You can say it's left its atom. But when doing so, it has to interact with all its other neighboring electrons. So that's how I get my electronic structure. Once I have this emitted photoelectron, it behaves more like a wave. And now this wave is leaving my central atom, and it's acting like ripples. Imagine throwing a stone into a pond, and you see these ripples go out, they hit the neighboring rocks, and then they start coming back. And you get this constructive and destructive interference. And that's what's building up my wiggles in the XAVs region. It's the atomistic interaction. And with some heavy math, I can back out structure from those waves. But in the lab, I have a really good unit for determining how a catalyst performs. And at the beamline, I have a really good unit for telling me how the structure looks. And I'd really want to know, how do I put these two together? I'm clearly not getting Exxon to move a 10-story reactor into our beamline. And I'm clearly not building a synchrotron at every chemical plant or every university out there. So there's a class of characterization that is referred to as operando characterization. This is the catalytic reactor at the beamline. What you can see is our synchrotron and our X-rays following the tan line has our ion chambers, which are our detectors, so we can measure the X-ray spectra, but instead of just putting a single sample in the beam path, I put a little reaction cell. And I can feed gas in, I can change its temperature, and I can see what's coming out in products with the gas chromatograph. And so I now have the ability to simultaneously measure product formation as well as structural changes. And if I do this with time, I can understand how a catalyst evolves. And so I then pose the, if that's what it looks like, how do I actually do it? And there's a bit of a history to this. So if you were at a playground, do you bring your own swing to the swing set? No, you assume there's a swing there. Well, 15 or so years ago, it was standard for if I wanted to do an operando characterization, I have to pack up my lab at UC Davis with all of the equipment, drive it to the beamline, set it up, and perform an experiment. It's daunting, and it has some risks, right? Say I'm shipping equipment, and I have a piece of equipment. If it breaks, I can't do the experiment. Bummer. 4 days of beam time wasted. Sad. You can't go. It's raining at the playground. The other issue is as you take apart and rebuild these experimental assemblies, you introduce contamination from things like air getting into the lines. And so this means the result you measure in the lab might not be the result you measured at the beamline just because of a little bit of cross-contamination. So we pose, how do you address these? And this is where, again, field of dreams, the feel-good story of if you build it, they will come. We want to build a park that does this. So the DOE's Chemical Science Division plus SSRL for the past 10 years has been prioritizing catalysis science. And it started with the setup of the Consortium for Operando and Advanced Catalyst Characterization via Electronic Structure and Spectroscopy. A mouthful. In short, it is CoAccess. This is a team of scientists led by Simon Baer. I am part of it. We have R.A. Jiyun Hong, engineer Jorge Perez Aguilar, postdoc Enrico Tusini, and externally, Dr. Fernando Villa. And our job here is to merge X-ray science and catalysis science and facilitate catalyst characterization at a beamline. This is, we are embedded at the synchrotron. We are here to lower that learning curve, make sure you design the right experiment, and you get the best data you can. The way we do this is collaborating with the users to see what are their needs from a catalytic standpoint, and how do we make that merge well with our beamlines. So we spend a lot of effort developing operando cells because every chemistry is slightly different. You might need different flow paths. You might need a liquid phase, a gas phase. If you're doing different techniques, you might have geometries that are restrictive because of the X-ray source. And so there's not one cell to rule them all. There's options. And picking my cell is like picking a ride at a playground. Do I want to climb? Maybe I pick a spectroscopy cell. Do I want to swing? Maybe I'm going to the imaging beamline. I want to use a slide. I got to climb and slide at that. So maybe I'm going to pick a capillary cell that allows me to do 2 techniques at once. So we're trying to get a sense of targeting specific areas based upon everyone's needs, likes, and wants. We spend a lot of effort building in situ or support equipment. Right? I've told you that we can put a reactor in the beamline to get X-rays in and gases or reactants through, but there's a whole set of infrastructure that has to be built up for safety. Can I properly dose a toxic or flammable gas into the system? When you show up, is it hard to interact with? I want something that's point and click, that when you look at it, it's very familiar. I know that that schematic, or that little image represents temperature. That little image represents a valve. Having it already in-house means that setup and teardown, moving it between beamlines, is far more efficient. We have control over it. There's no shipping risks. And when we make it portable, it allows us to take the same reactor system to different beamlines. And this helps us improve rigor and reproducibility as we don't have to think about things like a chemical engineer might about flow regimes. I took the exact same setup and moved it. I don't have to question of, was my flow different? It's just, what does the X-ray show me on a different scale? Finally, probably the biggest part of our day-to-day is education of the next generation of scientists. Synchrotron facilities, I didn't know what they were when I was a grad student until I got tossed into one, are high-energy physics facilities by nature. Catalysis scientists are often chemical engineers, and this is probably the biggest gap in terms of the engineering science world that you run into. And so we try to educate both sides to understand the needs of the other. And so this is explaining to the catalysis researcher, if you have a scientific question, how might a synchrotron help answer that? What is the appropriate technique? You have beam time. You show up, you're green, you've never been. It's a daunting experience. We're here to help kind of shepherd you in, show you the ropes, teach you how to use the machine, look at the data and decide good, bad, or what adjustments do I need. You spent 4 days, little sleep, you go back. You now have a mountain of data that you remember learning something about, but you don't know what to do with anymore. We hold workshops and camps where we invite students out to come work on your data so you get hands-on interaction with the scientists to bridge both worlds. And finally, when you're ready to write it up, we're there to help you pre-review your manuscripts to make sure you're using the right terminology and you're representing the spectroscopy or X-ray results in an appropriate manner so that it has a higher success of getting through the publication process. And so, good, sorry, I'm checking time. So with this, I wanted to give you 2 examples of how the users we interact with, co-access, the group I'm part of, and SSRL, the synchrotron I work at, work together to understand how COX, carbon dioxide, carbon monoxide, can be used for alternative fuels compared to our fossil fuel sources. I'm going to pose this in the power to liquids sector. So this is the idea that we can use alternative fuels like wind, solar, hydro to generate hydrogen through water splitting, well-established process. We burn fuels, and so we know there's a bunch of CO2. CO2 is a carbon source. If we can get that carbon back into a usable fuel, we can then burn it again, and the cycle becomes cyclic. So predicated on the idea that I can get a hydrogen source in CO2, the first thing I would do is do something referred to as reverse water gas shift, RWGS, which I'll talk about in a second. So that's CO2 to something, sorry, a reverse water gas shift, CO2 to CO. Once I get CO, I can use more hydrogen into a gas blend referred to as syngas or synthesis gas. And I can use another catalytic process called Fischer-Tropsch synthesis, where I can take that carbon monoxide and start chaining the carbons together to build bigger hydrocarbons. Once I have a hydrocarbon, it is a sustainable liquid fuel, and it can fill voids in the energy sector, such as aviation and shipping, where things like batteries might not necessarily be an economical or viable solution. So my 2 examples will focus on first CO2 to CO using a rhodium catalyst. The second example will CO to hydrocarbons. And we're going to pose the question for both of these of how does the structure, how does catalyst structure and performance change with time? Because I want to understand the dynamics of it. So as seen by a few slides already, the reverse water gas shift reaction has a competing reaction. This is CO2 methanation instead. So if I am planning to do reverse water gas shift, I should have dispersed or atomically isolated rhodium. During the reaction, if my rhodium sinters or I make the material start with a rhodium particle, I'm doing methanation and not driving my reverse water gas shift anymore. So the hypothesis is if I'm running my reactor and I see methane formed and rhodium particles, I shouldn't have CO. So I go to the beamline, and we're going to work left to right here one by one. So my left is a set of Zane's